It seems that we are live. Welcome everybody to this new coffee break with Eddyfi. My name is Frederic Reverdy, and I am with the M2M business unit here in France. So let's start. All right. Okay, so today we're going to talk about TFM, obviously total focusing method, and we are going to look especially at corner modes. Here is my email address in case you have some questions after and you want to ask me, or you can use the chat room here in YouTube if you have any questions, and I will try to answer them after. All right. Okay, so when it comes to TFM, according to ASME, it is possible to image defect through a multiplicity of modes. What is a mode? A mode is a different ultrasonic path. So it can be a direct path like LL, LT. It can be a corner path, which is what we're going to talk about today. It can be an indirect path, which is the one like LLLL, so L, 40. So essentially 4 layers. So we are most familiar with direct modes. Direct modes are pretty straightforward. We start from any transmitter, so any element that fires. We propagate through the component with either L or T, go to a pixel of the region of interest of the TFM, and back to all the receivers using, again, L or T wave type. So we have 3 possible modes, LL, TT, and LT or TL, which is essentially the same mode, but we rarely see this one. The main applications for the direct modes can be HTHA, so high temperature hydrogen attack. We have an image right here. We have like really small cracking, like 20 to 50 micron. We can use it for corrosion mapping, and we can also use those modes for weld inspection. So here is a multi-group TFM inspection using the new capture 3.2. All right, so we also have the indirect modes. So the indirect mode involves 2 reflection of the back wall. So we propagate through the component, have a first reflection of the back wall, go to the pixel, back to the back wall, and back to all the receivers. So you have 4 letters. We have typically we use the 4L or the 4T, but you have to know that you have typically up to 16 indirect modes. So we rarely use 16 indirect modes. Typical application is looking at bevel after reflection on the second leg. So like a typical here, it's a crack along the bevel. But today we're going to talk about corner modes, also called self-tandem by others. So these corner modes involve, again, propagating through the sample, 1 reflection of the back wall to the pixel and directly back to all the receivers. So you have 8 possible corner modes. I'm listing all of them here, but we rarely use all of them. And I would say mostly right now we are limited to like 3T or things like that due to like comprehension of those modes. What are the typical applications? It's detection of planar defects, such as lack of sidewall fusion or cracks. We are really looking at, those modes are really looking at specular echo perpendicular to this planar defect. So those are typical images you can obtain with corner modes, like a 3T here for a notch along the back wall, a TLL for a notch in the midsection of the weld, or a TTL for like these types of inclination. And what we like about those modes is they tend to draw, between quotes, the defect. It's very similar to like a lack of sidewall fusion on the second leg. When you use PUT on the second leg, you have your perpendicular to the bevel, and you have this nice specular echo. So this is typically what these corner modes do. So actually looking at an elliptical defect right here, we move the probes this way. So you have the TFM here. And when you look at the front view, you actually draw nicely the shape of the elliptical defect. If you drop this into the 3D view and superimpose that to the defect, you really see that we're able to image the defect perfectly. So there is some potential to those defects in terms of imaging. But there are things to check, to make sure we do properly. So typically, a corner mode is very similar to a pitch catch mode with TFM, with PAUT, using the same probe. We have a direct pass right here, a reflected pass right here. So when we go T, and T that we combine to a direct T this way. So at the end, what you obtain is this highly focused point, because we are using TFM, so we are focusing everywhere within the region of interest. So this is the path that this 3T mode is taking to reach that pixel. And for that particular configuration, we have a focal point of about 2.7 millimeter by 2.3. So this configuration is using a 5 meg probe, 64 element, shear wave, obviously, and pitch of 0.6 millimeter. So the focal beam is a little bit bigger than if you purely use a TT mode, because you are looking at kind of the intersection of the reflection and the other one. So this tends to elongate a little bit the focal point. The 3T tends to have a preferential direction, which is the bisectrix between the direction after reflection like this one and the receiving angle. So for this particular pixel, the direction of the energy is pretty much horizontal. It's kind of going this way. So meaning that we are going to be sensitive to defects perpendicular to that direction. So this is important because the corner mode are kind of looking for specular echoes. So let's look at how this direction evolves as we move our focal point along a vertical line, kind of following a vertical defect. So here we are starting here. We see that the direction is going this way. Now we are pretty much horizontal, so sensitive to vertical defect, starting to go up a little bit and higher and higher. So the higher the focal point, the higher the direction of the energy as well. So the less sensitive we are to vertical defect. Also, we see that we have less energy, less field energy on the top compared to the bottom. So if we were looking at a vertical defect, we will tend to be more sensitive right here, where the direction of the energy is horizontal, as opposed to here. So that's why there was a tool that was developed. There's many names, sensitivity map, others call it acoustic influence map, or AIM. So it was first developed by my colleague, Combo Ceci, in her PhD. So you have here a link to one of her publications. So she's still with us at M2M. And the idea of this sensitivity map is to kind of draw within the region of interest of the TFM the sensitivity of one mode, so here the 3T, to one defect orientation. So here we are only looking at purely vertical defect all across the region of interest. And we see that for this configuration, the one we have selected with the probe in the region of interest, we will be very sensitive right here. Like if we had a vertical defect right here, we'll have a pretty good signal-to-noise ratio. But if the defect was up here, that mode would not be sensitive to it. Why? Because if we go back to this, because the direction of energy is going this way, and we are looking at vertical defect, so we wouldn't have any specular echo. This is only one direction of defect. So this is very important to remember. So what happens when we have vertical defects? What can we expect in terms of sizing? So let's say we have an 8 millimeter notch. We are still within the red region of our sensitivity map. We look at the 3T mode. So like we draw nicely using the envelope. It's perfect. And if we look at an echo dynamic, so we look at the energy along the z-axis, we can see that for this 8 millimeter, we have about 5 dB drop. It's actually 5.2. So it's not very far to our typical 6 dB drop. So we could potentially use our 6 dB drop as long as the defect is within this highly sensitive region of the region of interest. But what happens if our defect is a little bit taller? So let's look now at a 15 millimeter defect. So the defect now is reaching into kind of the green region. We look at the TTT TFM image, and we see that we are still drawing our defect. But when we look at the echo dynamic for the 15 millimeter, there is actually a 9 dB drop. So we cannot really use a 6 dB drop anymore, because if we were to use a 6 dB drop here, we would undersize our defect. We will actually measure about 13 millimeters. We'll make 10 to 15% error on measurement, just because the defect is not in this region anymore of the sensitivity map. So when it comes to sizing using corner mode, it can be an issue. and you have to really make sure that your defect, knowing the orientation, is within the part of the sensitivity map where there is very small variation in amplitude. So I said before that this sensitivity map, or AIM, is calculated for one direction. So this is what we have for 0-degree defect. So here, looking at a vertical defect, let's see how this sensitivity map evolved as we are changing and tilting the defect. So I'm going to do it by a step of 2 degrees. So the same map, but for defect with a 2-degree fall. And we can see that the sensitivity map is going down, meaning that our TFM, our 3T mode, wouldn't be sensitive to any defect right here. It will be very sensitive to the bottom of the TFM image. So if we have this 15 millimeter defect, or even here 8 millimeter defect, we wouldn't be sensitive at all. And to illustrate that, I mean, in real life, it's hard to predict the orientation of defects. Unfortunately, they are not like these nice notches that we like. If you look at weld prep, according to welding standard, you have a tolerance of plus minus 2.5 degrees. So you already have a 5-degree gap on the bevel itself. So let's look at 8 millimeter notch right here, and let's look at a reconstruction of a 3T mode for the defect evolving from 0 to 10 degree. And here we're going to do the TT mode, so the direct mode, but we are going to display the first leg and the second leg. So essentially here we are doing the TT, and here the 4T on the same image. And for the, at 0 degree, we can see this nice corner echo and the tip diffraction here on the first leg, tip diffraction on the second leg. And this is what we are going to look at, how this changes with defect orientation. And here we have our 3T mode for the 8 millimeter defect, the same image we had before. So let's see how it changes. Now we have 2 degree, barely any changes. 4 degree, we can see that we are losing amplitude right here. 6, losing a lot of amplitude right here. 8, and 10 degrees. So you see how the 3T mode was okay at the beginning and starting to lose amplitude. If we look at the TT, at 10 degrees, we still have our corner echo right here with the defect. We can see that our tip diffraction on the first leg is located perfectly with the defect. On the second leg, it's shifted a little bit. But going back to even 4 degree, we can see here that there is a drop in amplitude on the higher part of the defect. And if you remember the sensitivity map, it's because as the angle of the defect goes up, the sensitivity map was kind of going down, being less sensitive to this part. While the TT mode is still okay to measure the defect. Of course, you have to make sure that your tip diffraction has enough sensitivity itself, 12 dB or more, but we'll see examples before what this is typically not a problem. All right, so let's look at sizing of what I just did with the TT mode based on tip diffraction and corner echo, and a minus 6 dB drop for 3T. For 0 and 2 degree orientation, this is good. We measure the height of the defect perfectly. The TFM pixel size is 100 micron, so this is within the tolerance of the precision of the TFM. But starting already at 4 degree, the TT mode is okay, but the 3T mode is starting to undersize it, and then after it quickly undersizes it down to 1 millimeter, which will actually be the size of the focal point at the bottom of the screen, of the TFM. While the TT mode is sizing perfectly, 7.9 is still okay because we are not looking at this distance, we are looking at this distance. So for 10 degree defect, that distance is 7.9 millimeter. So we see that a slight misorientation, I mean 4 degree is not a lot, we can lead to a huge undersizing using the corner mode. So when it comes to real defects, again, they are not this smooth, nice defect. They tend to have multifacets when they propagate. And we have a weld here. It's a 1-inch weld with a defect that initiate here, close to the root, and start to propagate this way, kind of vertically, and then follows the bevel. And so we have here the TT mode with the first leg and second leg. So again, this is the TT and this is the 4T at the same time compared to the 3T. So let's switch to capture. So here I have my TT, 3T, So if we wanted to size this using the TT mode, so I'm going to go here. And I kind of see, I'm going to zoom a little bit, kind of see that I have a tip diffraction right here that I see here. I'm going to increase the gain, and I can actually see that I have a signal-to-noise ratio of about 20 dB. So I have pretty good signal-to-noise ratio here. So to size it, I will essentially position it on the maximum of the tip diffraction here, and I will do the same on the corner echo. So I'm just going to go roughly. It's kind of roughly here. I will need to do it more accurately, obviously. And my delta depth here is about 6.5 millimeter. So here the height of my defect will be about 6.5 millimeter. Now let's look at the TTT mode. And here I'm displaying the echo dynamic along Z. So I'm projecting all the maxima along the Z axis. So here I have my maximum right here. You can see this is right here. I'm going to zoom. I'm going to position my blue cursor to have 6 dB. So I have 6 dB between my data cursor and my measurement cursor. And I'm going to put one right here. My blue cursor is at 0. So I can see that the height of my defect is 1 millimeter, which I know is not the case because I just measured it to be 6.5 millimeter. The problem here is my 3T mode, due to the face of my defect, is not representing the defect nicely. It's not drawing my defect nicely. And even if I was to kind of use that as kind of the top of the defect, we see that we are still not measuring the height of the defect properly. So really, we have to be careful when using this mode for sizing purposes. The amplitude right here of this echo is about the same as the amplitude of the corner echo. All right. One other aspect to pay attention to when using corner modes is thickness. Because they rely on a backwall reflection, they are very sensitive to the thickness input you input in your algorithm, so in your system. So to illustrate that, I'm looking at a 3 millimeter notch image using a 49 millimeter thickness. So the original thickness is 50 millimeter, but I'm telling the system I only have 49 millimeter. So I'm making a 2% error on my thickness measurement. So here, this is my TT with my 4T again, and this is my 3T. So I'm telling my system my backwall is here, but actually the real position is this one, kind of the center of the corner echo. So I'm making this 1 millimeter error. So if I want to size it using TT, I will look at the maximum of my corner echo, maximum of my tip diffraction, and I will measure the height of my defect, and I find my 3 millimeter. Here I'm telling my system I'm at 49 millimeter, the real thickness is 50. When we use corner modes, we don't calculate anything outside of the component because they assume a reflection of the backwall, so there is no reason in calculating pixel outside. So if I now use a 6 dB drop, I'm only sizing at 2 millimeter. So essentially, I'm making an error which is the same as the error I'm making on my thickness measurement. So you see that it is, when you do corner mode, it is very important to input the perfect thickness of your component. Kind of to illustrate all of what I've said before, we're going to look at the 5T mode. So the 5T mode, I think I will classify it as a corner mode as well. It is very similar to the 3T mode, except that it involves an extra reflection. So we have one reflection of the backwall, one reflection of the surface, back to the defect, back to the backwall, and back to the probe. So it is the 5T, in the same way as the 3T, is effective for vertical defects, but located on the same side as the transducer. So we are kind of going to look at the same influential parameters as 3T. So essentially, defect orientation, thickness measurement, using like a 3 millimeter notch this way. Actually, this notch. So I kind of adjusted my index offsets to make sure that I have a good sensitivity map, not sensitivity map. I can see here that for that particular position, I have, for the defect right here, I have very small variation of sensitivity. Again, remember, this is for only 0-degree defect. The map I'm drawing right here is only for 0-degree defect. Anyhow, it seems that I have good coverage of my area looking for vertical defect. For the TT mode, this is what I'm calculating. It's kind of overkilling right here, but I'm using this entire TFM box right here, which in a sense would be a TT, a 4T, and a 6T. So I'm looking at my defect right here, kind of on the second leg. So this is the result I have for my 3mm notch. I'm going to do a zoom. So I'm making a zoom of this area right here. So I have my corner echo, I have my tip diffraction on the second leg. This is my tip diffraction on my third leg. And this is my typical 5T mode reconstructed after a rebound. So sizing is kind of exactly the same. I will be using tip diffraction to corner echo for my TT, and I will extract my 3mm. Here I'm going to use a 6 dB drop, and I will size it at 3.2mm, which is pretty much the same as 3mm. My pixel size is 100 microns, so I will say I'm within close to be within my tolerance of my grid. So now, again, let's look at what happened when we start tilting the defect from 0 to 10 degrees. And here I'm only using a 3mm defect. I'm not using a very high defect again. I'm trying to use a small defect. And kind of the same is happening right now. We see that the TT mode, I have my corner echo, I have my tip diffraction here positioned correctly. Again, my tip on the third leg is not necessarily positioned correctly, but I don't really care. I will be using this one and this one. And we see here that on the TT mode, I have completely full separation. Don't draw my defect anymore. And even this kind of diffraction is not located in the right location. So if I go back here, I use a 3mm notch on purpose. I really wanted to stay within this contained region here of my sensitivity map. I didn't want to have a long defect. I just wanted to see the influence of orientation for defect that's really, really close to the top surface. So we see that kind of the same way as the 3T. Quickly, even at 4 degrees, we lose amplitude here, and we are not sizing our defect properly. So the error is kind of the same as the 3T before. I'm not going to put it here. But okay. So now let's look at the sensitivity of the 5T on thickness measurement. And I'm going to use the same mistake I made before. Instead of 50, I'm going to put 49mm. But now I have one reflection of the back wall, one reflection of the top surface. So I'm going to make the mistake twice. So instead of making a mistake of 1mm, I'm going to make a mistake of 2mm. Again, on the TT mode, I have my corner echo and I have my tip diffraction. If I measure the distance, I still have my 3mm. So I'm not really sensitive to my variation of thickness. What's happening here on the 5T is interesting. It's a little bit different compared to the 3T. Actually, like this 2mm error, so which would be a kind of 4% of the travel path, my defect is supposed to be here. And now it's kind of positioned after. It's not even positioned at the right location, which is okay. It's not a big deal if I'm not positioning the defects at the right index position. But if I do my -6 dB drop, so I have my echo dynamic here, 6 dB, here I would be oversizing my defect if I'm only using this and if I'm not using that information. So we see here that the 5T is even more sensitive to errors we are making on the thickness measurement. All right. So I'm gonna conclude. We are making shorter coffee breaks. So TFM offers the advantage of seeing defect through different modes. We have the direct mode, we have the indirect mode, we have the corner modes. There is potential here. And some tools such as sensitivity map have been developed to help operators see a sensitivity of some modes within the component thickness. But I really want to put some stress here, but on that, you really have to know the limits of those modes. They are highly sensitive to defect orientation and to component thickness. So before using them, you really have to know your components and kind of like the preferential direction of your defect. Otherwise, it's going to lead to quickly to undersizing, and undersizing is not permitted per code. All right, thank you for your time. I was 20 minutes, yeah, I was right on time. So I'm going to take some questions. So what would be the technique to size defect with corner mode? So this is a difficult question, typically because we are looking at specular echoes. I will tend to use a -6 dB drop, but to do that, you really have to make sure that you are within the region of the sensitivity map where you have very low variation. And the difficulty here is that to do that, you have to know the direction of your defect, because you have to draw the sensitivity map associated to the orientation of your defect. So it is really complicated to use those modes for sizing. Is an acoustic influence map sufficient to predict the sensitivity of one mode? It is, but only for one orientation of defect. So if you don't know the orientation of your defect, the aim or sensitivity map is not sufficient to predict the sensitivity you're going to have in your configuration. So it's a tool. It's one of the tools that could be useful, but that's not sufficient. Looking at your screen, it looks like the TT mode is sufficient when we will use the corner mode then. Okay, so yes, in my opinion, for when you are dealing with weld on a plate or circumferential weld, probably the TT, obviously using the first leg and second leg, would be sufficient in most cases. The 3T, if you add it on most system, it would probably impact also your productivity, because you will need to add some modes, so it's going to also impact your productivity. So the corner mode like the 3T could be interesting when you are dealing with very tiny defect close to the root. When you have the root here, you tend to have a corner echo due to the root echo, and you are not going to see a tiny vertical defect. So like a TT mode will be very sensitive to that, and you will see that nicely on a C scan or D scan. Also, if you are dealing with welding processes that are purely vertical, like for example, laser welding, electron beam welding, or if you are doing any HDPE, so high density polyethylene with a hot plate, it's a purely vertical fusion phase. So here you actually know perfectly that you have a vertical fusion phase. So if you are looking for lack of fusion, you can use a 3T mode because you know exactly your the orientation of your defect. Obviously, as you have seen in the presentation, you will still need to make an accurate measurement of your thickness before you do that. But those will be the cases where I will be using a corner mode. For the rest, I will probably stick to the direct mode, TT, again with the second leg. All right, I think that's it. I don't think we have other questions, guys. So if you have any questions, please send us some emails, or you can go on the YouTube page when it's going to be published, and you can ask questions there, and we'll try our best to answer questions. And if you have any suggestions for some presentations that you would like to see, don't hesitate as well to ask, and we'll try to organize some coffee breaks like this. All right, thank you, and see you next time.